Hello students, welcome back. Previously we went through the computation of definite integral using the fundamental theorem. Basically we have to use this after finding out the antiderivative function, capital F. And the typical method was kind of like this. Prepare the antidifferentiation and then get the antiderivative without plus c, no need for plus c, and then use this bracket expression as a shorthand of the fundamental theorem, yes to be used, and then use it. Plug in the top, plug in the bottom, subtract one from the other, and then what you have the answer. So this kind of preparation for the antiderivative is essential. And the antiderivative itself, of course, that's essential. And the fundamental theorem, another essential step. The others are expendable, especially last two lines. Now let's go to the other aspects of the fundamental theorem. This time, let's consider the derivative of the definite integral. We begin with a function defined as a definite integral, like this. And here, it doesn't matter which variable I have here, as long as this is not x. It could be t, or it could be u, or it could be y, or it could be z. It doesn't matter, because it's gonna disappear anyway. For that reason, this variable here is called a dummy variable, but I don't like that term very much. It's, anyway, never mind about that. It's old expression. People are not that sensitive about disability in other people. Anyway, in that case, basically, the derivative of integral is the original function back. Let's go through with an example problem. Here's a typical example problem here. Let's see. A little bit bigger font will be helpful, I guess. We have denominators and powers and stuff. Okay, we want to find out the derivative of the integral. And basically, we are doing this. By the fundamental theorem, integral is antiderivative. And if you take the derivative of antiderivative, you get the original function back. The only thing that you have to worry about is we have to get correct variable x. So do not try to take the derivative of this thing here. The answer should be just this function, except that the variable should be x. And that's it. It's that simple. If you try to find out this integral, it's not impossible to do it that way, but it's going to be very difficult. Yes, it works, but it's going to be hard. If you try to take the derivative of this, then that's going to be automatic 0 credit. You see? If you take the derivative of antiderivative, you get the original function back. But taking another derivative, that's the order of second derivative. That's completely incorrect. That's all there is. Just plug in. The only difference is change a variable from x to y. Y to x, sorry about that. And if this original problem had been not in terms of y, but for some other character, such as say t, or anything else as a matter of fact, anything other than x, what's the answer? No difference. Same thing, just replace that variable by x. That's how you do it. How about the justification? Well, justification is this fundamental theorem. This is capital F of x minus capital F of a, where capital F is the antiderivative function. And if you take the derivative of this antiderivative, Well, this part is constant, so that one just goes away. And you just get f prime. But f prime, that's the original function, because that's the antiderivative. Derivative of the antiderivative. It's that simple. But if you're not really comfortable with proofs, then just think of it as just plugging in. Now, what if you apply some manipulation? Again, I need a little bit bigger font. What if I apply some manipulation? Am I going to get the same thing as before? Just x and x? The answer is close but no cigar. Something is wrong. How do you make it right? There you go. That's how you made it right. Why? Because, let's see, x is up there. Now x is down here. So this whole thing, as a matter of fact, can be rewritten like x2, and then we need a negative sign because we switch the top and bottom. And then this one is just the same as before, just plugging in. If you're interested in the proof, let's go back here. If you have, okay, let's copy and paste it here. If you have a here and x down here, then this will be a, and that's f of x, and this is 0, and then f prime of x, and that's the original function. Oopsie. Now okay. So we may have to worry about the negative sign if we switch these two. Now, case number 3. What if I have something this complicated? Both the top and bottom are functions. Well, I haven't written this level of problem in applied calculus, and probably I won't, but in STEM calculus, I usually do. This is important, especially for next level, calculus 2, and then differential equations and things like those as well. And all the engineering students need is, this is absolutely required for all the engineering students, so I usually cover it in STEM calculus. But in applied calculus, I usually don't. That said, here's a formula. If you have functions both top and bottom, I guess I need bigger font again. Plug in the top, plug in the bottom, but then again, by chain rule, you have to multiply the derivative of the inside. Derivative of the inside. Here's a proof. So the integral is capital F of b minus capital F of a by the fundamental theorem. But a and b are functions, so capital F of b of x minus capital F of a of x. Okay? And then we take the derivative. By the chain rule, we get the derivative of the outer function times the derivative of the inside. It's a chain rule. Derivative of the outer function times the derivative of the inside is a chain rule. And the derivative of outer function is nothing more than the integrand, the original function. So original function, plug in, and chain rule, minus original function, plug in, and then chain rule. So if you apply that rule to this problem, what are you going to get? Stop the playback and try. Done? Well, here we go. Plug in the top, which is blue, so we get this. And then we have to multiply the derivative of the inside. The derivative of x squared plus 2x is right here. Minus, plug in the bottom. Well, over here, plug in 2x minus 1. So that's what we have. And then we have to multiply the derivative of the inside. Derivative of 2x minus 1 is 2, right here. So it all follows from this formula here. This formula will turn out to be very, very important for applications, especially in differential equations. And a lot of systems and physics and engineering are built upon differential equations. So for STEM calculus, this is essential. For applied calculus here, I'm not so sure about that. Okay, all right. So much for section 2.